Welcome to the channel. In this video we are going to discuss mathematical induction important problems. So suppose if you are watching this is the first time the channel, please like the channel, share the channel and also subscribe the channel. Now entering into the problem, here the question is given, prove that by using mathematical induction 1 square plus 2 square plus 3 square plus and so on plus n square. Prove that by using the mathematical induction 1 square plus 2 square plus 3 square plus and so on plus n square is equal to n into n plus 1 into 2n plus 1 whole divided by 6. So how to prove this is by using the mathematical induction. We know the procedure of the mathematical induction. Whenever the statement is given, to prove that is by using the mathematical induction. So we can solve this problem by using 3 steps. The 3 steps are, in the step 1, you have to prove that the statement is true for n is equal to 1. And step 2, we have to assume that the statement is true for n is equal to k. And in the step 3, we prove that the statement is also true for n is equal to k plus 1. So when you prove like that, then finally we can say that the given statement is true for, so for all small n belongs to, by using the finite principle of mathematical induction, the given statement is true for all small n belongs to capital N. Now, what is the solution? How to find the solution? See here. Now, what I am doing is let S of n, the given statement, let S of n be the statement that, so what is the statement here? This is on the given problem 1 square plus 2 square plus 3 square plus and so on plus n square, so which is equal to n into n plus 1 into 2n plus 1 whole divided by 6. Now what I am doing is here, in the step 1 is here, so you take in the step 1, put n is equal to 1. So where we have to put in n is equal to 1? In the LHS and RHS. See here we have LHS here, n squared. So in the n squared, if you put n is equal to 1, so we get 1 only. So in the RHS we have, so n into n plus 1 into 2n plus 1 whole divided by 6. In this, if you substitute n is equal to 1, then here 1 into 1 plus 1 into 2 into 1 plus 1, so which is whole divided by 6. Now again here 1 into 2 into 2 plus 1 is 3, so that is 6 by 6, so we get 1 here also. So now here we can consider that, so therefore LHS is equal to RHS here. LHS is equal to RHS. So when LHS is equal to RHS, the statement is true for n is equal to 1. So therefore S of 1 is true. Now in the step 2, you have to assume that S of n, the statement S of n is true for some n is equal to k. For some n is equal to k. What is k here? Where k belongs to the natural numbers. Now in the step 2, that is S of k is equal to 1 square. S of k is equal to 1 square. In the given statement you replace n by k, 2 square plus 3 square plus and so on plus k square which is equal to k into k plus 1 into 2k plus 1 whole divided by 6. Now in this, so k plus 1th term finding. So k plus 1th term is equal to. So from where we have to find the k plus 1th term? From the kth term we can find the k plus 1th term. Here kth term is k square. So replace k by k plus 1. You get the k plus 1th term in the kth term. So from the kth term we can find the k plus 1th term, which is k plus 1 whole square. Now you say this s of k is equation 1. So now here in the step 2, after finding the k plus 1th term, now in the step 3, what is step 3 here? In the step 3, we have to prove that s of n is also true. S of n is also true for n is equal to k plus 1. So now for this purpose, so how to prove that the given statement is also true for k plus 1 means wherever in the s of k, there we have to get, wherever k is there we have to get k plus 1. Then we can say that, so the given statement is also true for k plus 1. In the s of k, wherever k is there we have to get the k plus 1. Then if you get k plus 1 wherever k is there k plus 1, then we can say that the given statement is also true for n is equal to k plus 1, or simply we can say s of k plus 1 is also true. So for that purpose what I am doing is here adding k plus 1th term on both sides to equation 1. So for this equation on both sides adding k plus 1th term. Now what do you get? So 1 square plus 2 square plus 3 square plus and so on plus k square. For this left hand side, adding k plus 1th term, that is k plus 1 whole square, which is equal to the right hand side we have here. So k into k plus 1 into 2k plus 1 whole divided by 6. So k into k plus 1 into 2k plus 1 whole divided by 6. And for this also adding k plus 1th term, that is k plus 1 whole square. Now what I did here, I added k plus 1th term on both sides to equation 1. Now what I have to prove? It is enough to prove that, so the right hand side of the condition, every term must be in terms of k plus 1. Now simplifying here the right hand side by taking the LCM 6 here. So now we get here, this is k into k plus 1 into 2k plus 1. So plus 6 into k plus 1 whole square. K plus 1 whole square. Now after taking the LCM, now which becomes k into k plus 1. So into 2k plus 1 into plus 1, 2k plus 1 plus 6 into k plus 1 whole square. So now simply we can take the k plus 1 common here. In both we have the k plus 1. So when you take the k plus 1 common, we get here simply k into 2k plus 1 and plus 6 into k plus 1 we get. 6 into k plus 1 whole divided by 6. What is our aim? We have to prove that wherever k is there k plus 1. So which is equal to, this is here, k plus 1 into here, when you multiply this is, so 2k square and k into 1 is k plus, this is 6k, so plus 6 whole divided by 6 again. So now we get here k plus 1, So into here 2k square plus 7k plus 6. So whole divided by 6, which is equal to k plus 1 into here. When you factorize this is, we get 2k square. So here 4k plus 3k and plus 6 whole divided by 6. So when you take the, so 2 common here, k plus 1 into, we can take here 2k common. When you take 2k common, we get k plus 2 here, and plus when you take the 3 common from these 2, we get 3 into k plus 2 whole divided by 6. So finally, if you see that, when you take k plus 2 common here, we get k plus 1 into k plus 2 into, so 2k plus 3 whole divided by 6. Further, to write every term in terms of k plus 1, here this is writing k plus 1 into this is k plus 1, and here this 2k plus 3 is also writing as 2 into k plus 1 and plus 1 whole divided by 6. See, observe here, whenever k is there, we get here k plus 1 and k plus 1 and also 2 into k plus 1. Here 2k plus 2 plus 1 is nothing but 2k plus 3. So therefore finally we can write s of k plus 1 is also true. S of k plus 1 is also true. So therefore finally we can write by the principle of finite mathematical induction. So S of n is true for all small n belongs to the capital N. See, like this we can prove by using the mathematical induction, the given statement.